Okay, so hello everyone. I will present you Dr. Jakub Ripa. Jakub received his PhD in 2011 at the Charles University in Prague, where he worked on the study of gamma ray bursts. He was then a postdoctoral researcher in Ewha University in Seoul, South Korea, Sungkyunkwan University in Suwon, South Korea, and National Taiwan University of Taipei, Taiwan, where he worked on the UFFO Pathfinder satellite instrument for the detection of gamma ray bursts. In Taiwan, he also worked on the Taroji experiment for the detection of ultra-high energy cosmic rays, and on the Anita high-altitude balloon experiment to detect ultra-high energy neutrinos. He then moved back to the Charles University and to the Edvest University in Budapest, and he's now working at the Masaryk University in Brno, Czech Republic, where he works on gamma ray bursts and on the CubeSat instruments Camelot, GRB Alpha, VGIT, LUSAT, and Hermes scientific pathfinder. The most recent work includes preparation of the ultraviolet small satellite mission Cubic. Thanks.
Thank you, Ezekiel, and also thanks to Ricardo for inviting me here and giving me the chance to talk about our CubeSat missions and about the smallsat mission Cubic, which is now in preparation. So there is behind many people, so I list here a few most important from our collaboration. So the first I will talk about these CubeSats, GRB Alpha, VesulSat-2, and GRB Beta. The first two are already in space, detecting gamma ray bursts. The third one is in preparation. And the last part of the talk, I will focus on the ultraviolet mission Cubic, which is very exciting. It was approved for funding about a month ago. And so now we are in the initial phase of this mission. Still about 5 years ahead to launch. But it will be very important for observing kilonovae and doing a very exciting science. So let's start with GRB Alpha. It's a small CubeSat. It's only 1 unit size, so it's about 10 times 10 times 10 centimeter. You can hold it on one hand. It's about 1.3 kilogram heavy. It has a small gamma ray burst detector on board. As you can see here, the detector composed, it's on one side of the CubeSat. The effective area is about 50 centimeters squared. The detector is based on the cesium iodine scintillator, which is read out by 8 silicon PMs. There are figures of the mean effective area as the function of the direction, and the upper plot shows the effective area as a function of energy, also for different directions. So for the best sensitivity is on axis, reaches about 50 centimeters squared. But it's amazing that even with such a small detector, you can still observe the many GRBs a year. So this is actually just a technological pathfinder, because we would like to have a constellation of CubeSats called Camelot, which would be at least 9 satellites on low Earth orbit, monitoring GRBs, having the full sky field of view, and doing such a fine timing resolution that it could use the triangulation to localize the GRBs. It's similar to the Hermes project, but Hermes is more complex detector, which provides a wider energy range and better timing resolution. The detector, the heart of the detector is the cesium iodine scintillator, which is wrapped in the highly reflective foil, ESR. It has the 8 MPPCs split into 2 independent readout channels. These MPPCs are optically coupled with the scintillator with optical glue. Then after we assemble the detector, we figure out we have lots of stray light coming inside the detector, so we had to wrap the scintillator inside the optically thick Tedlar to prevent, to lower the noise due to the light going inside the scintillator and inside the MPPCs. one side of the detector is protected by 2.5 millimeter thick lead alloy, which is there to lower the dose obtained by the silicon PMs on orbit. Our satellite is on the polar orbit, so every day it passes about 10 times SAA, and it receives high doses of energetic protons, which slowly degrade the MPPCs and increases the dark current and increases the noise. So this helps to slow down the degradation process. The detector was, after it was assembled, it also went through it was integrated with the satellite, and it went through the environmental tests, through the thermal vacuum test, which was done in Slovakia. Vibration test was done in Budapest. There is a photo of the antenna deployment test. Then it was delivered to Russia. It was launched on the Soyuz rocket, which was before the war. So things looked nice at the time. It was like a collaboration between several countries. I didn't emphasize, but I should, because the detector itself was assembled in Hungary. We have collaborators from Slovakia and from the Czech Republic, many companies who build the satellite, and we build the detector. We also have a strong collaboration with the Hiroshima University, who developed the analog electronics and also helped with the calibration of the detector. And then the satellite was launched in March 2021 to about 550 kilometer altitude. We are using a radio amateur band. So when we are collecting data, we have our ground stations ground stations with our partners, like Technical University in Brno, Košice Technical University. We have also our antennas outstation built in the Piszkesteto Observatory in Hungary. But we are also using largely the SADNOX network, which is a radio amateur network with UHF antennas all around the world. And this helps us to drop data anywhere around the world, and we can collect this data and then decode the data packets. And it also helped us at the beginning, after the launch. The first sign that the satellite survived the launch came from the radio amateur in Australia, in Brisbane, which was just 5 hours after the launch, and we didn't need to wait 15 hours for the satellite to pass above the Central Europe, and we received the signal that the satellite is leaving relatively early. So far, we were successful in detecting many GRBs. Up to yesterday, it was 46 GRBs. We have 25 solar flare detections, 2 soft gamma repeaters observed. On this website, there is this university website. We have the list of all our transient detections. And I think this is a nice success, because the purpose of this mission was to just demonstrate how the detector behaves, demonstrate what is the lifetime of the detector, demonstrate that we can observe any transient, but we already have more than 70 transient detections. So we didn't hope in so many observations. This is an illustration of the light curves, raw light curves without any background subtraction. The blue curve are the GRBs observed with GRB alpha. It is compared with detections from other satellites like a SWIFT, Integral, or Fermi. One of the GRB was had a measured redshift 1.7, which is typical for long GRBs, nothing exciting. But it's really nice to see that actually this corresponds to about 10 light years distance. So even with such a small device, much smaller CubeSat, which you can hold on one hand, we can observe events which are in such a distant universe. Few GRBs were detected just several hours apart. So this demonstrates that the nano-satellites can be used to routinely detect the GRBs. And it's really possible to have a constellation of nano-satellites and observe GRBs really on the routine basis. We were really lucky that there was the brightest GRB so far observed, the brightest in the all 55 years old history of the GRB science, 221009A, and GRB alpha also observed this event. So these figures are this is actually a nice video which shows the bright GRBs observed by Fermi GBM. The brightest GRB, it got the name bold, is shown here. This is before the saturation, before the pileup was corrected on GBM. So this is the inferred total count rate, and all GRBs before are about 10 times less bright. It was also claimed that this is actually, when you compare the fluence of this burst and fluence of all previous detections, it seems that this event is 1 in 10,000 years. If you extrapolate the distribution of the fluences, which is a little bit hard to believe, because are we really so lucky? Or is there some population of another GRBs, or more bright or exceptional GRBs, which are just this can we really extrapolate this distribution? It's a question. It was also interesting GRB because there was 18 tera electron volt gamma rays detected by Cherenkov Observatory in China, which was the first time such high energies were observed from a GRB. And so with GRB alpha, we had detection in the 13 energy bands with only 4-second resolution, because this is our current limitation on the onboard software. We were not so lucky in the position. The satellite was near the North Pole, and the blue curve is our light curve from GRB alpha compared with the integral. This is the red curve. So the brightest part we observed nicely, but then the GRB alpha entered 1 Allen radiation belt, and the second part of the burst was buried under the background due to the trapped electrons in the 1 Allen radiation belt. The count rate for such a small detector, 50 centimeters squared, during the peak of the burst was about 22,000 per second for such a small effective area. We were able to also reconstruct the spectrum, how to fit the spectrum, and then we did it for the time before the pileup, because we had some moderate pileup at the peak time, and then from the scaling the flux, we were able to determine that the isotropic equivalent luminosity was higher than about 8 times 10 to 52 ergs per second, and isotropic equivalent total emitted energy was more than about 1.5 times 10 to 54 erg. So this we published in a paper with there were also several other observatories. Some of them had where detectors were saturated due to this burst. It was interesting GRB because it also affected the ionosphere of the Earth. There are also articles how this was measured, that effect of the ionosphere. So then several other papers cited our work, and the name of the GRB alpha, a small CubeSat, is mentioned next to large famous missions like Fermi, Integral, Agile. which is it's nice. We have just a small CubeSat. So next to besides detecting the GRBs and other transients, we are also monitoring the background of the low Earth orbit. These are the tracks of the satellite with the measured count rate at different energy bands, above 70 keV, above 100 keV, about 400 keV, 600 keV, where you can see several patterns from the outer 1 radiation belt at the north, around the north and south pole. There are these high intense backgrounds due to trapped electrons. Of course, there is also SAA. When the satellite is going through SAA and going north, then we can see a pattern here, which is increased internal background, activation background due to the trapped protons, which activate the detector and other material in the satellite. And then it decays. But you can also see here is a little bit increased. That's when the satellite goes this way. And we don't see the same thing when the satellite is actually going northward and then enters the SAA. We see it only when first it gets activated inside the SAA. So also this background limits our duty cycle, or the time where we can observe GRBs, because about 40% of the time we are in the high background region, where the background jumps up 100 times and it is impossible to detect any GRBs there. Another goal is to see how the detector is aging, how the MPPCs are affected by the trapped protons in SAA. This is part of our background spectrum at the low ADC channels, at low energies. This is a noise peak. And over the months, you can see how the noise peak is getting wider. And because that's due to increased dark current and the dark noise as the MPPCs are aging. Before the launch in the lab, we measured that our low energy threshold was around 10 keV. 2 years later, it is 60 keV, but still it's sensitive enough for detecting GRBs. We don't have any active cooling, so temperature is in the range of 0 to 20 degrees Celsius. Depends if it is in the shadow or illuminated by the sun. Here is the preliminary result from the GRB alpha and detectors on the VESELSAT-2 with two different readout channels on GRB alpha and 2 different detectors on VESELSAT-2. And this is the energy, the sensitivity threshold, the low energy threshold, as it depends on the number of days since launch. On VESELSAT-2, we have much slower degradation. We still need to understand why, but there can be several effects. The detector is, or the silicon PMs are more shielded on VESELSAT-2 because it is in the, they are placed in the middle of the satellite, and there is lots of aluminum and other structure behind from one side. Also, VESELSAT-2 is about at 20 kilometer lower altitude, and the temperature is about 7 degrees lower on average. But I think the main reason is the shielding problem. But this is something we need to understand, because on VESELSAT-2, it seems that the threshold is getting saturated. On GRB alpha, it is still increasing. Interesting is this break here. We don't have any deeper understanding right now. So this is the VESELSAT-2, which has 2 detectors, essentially same as on GRB alpha, placed perpendicular to each other, placed under solar panels. The solar panels were custom made with a lower amount of copper layer, so they are more transparent for high energy X-rays. Our detectors on the satellite are just a secondary payload. Is the main payload are the Earth observing cameras. There are one, and there is behind is another smaller camera taking pictures of Earth. So we have a lower data rate, amount of data per day we can download. But still, we also have many detections with the VESELSAT-2. These photos shows the analog electronics of the detector, the digital part, where the 2 channels per detector are treated separately. These are photos from the integrating of the satellite. And VESELSAT-2 was launched in January 2022, also to sun-synchronous orbit, initially to 540 kilometers, but now the distance is larger after more than 1 year in space, and the solar activity is increasing, so we can see that the satellite is going down faster. With VESELSAT-2, we have about 30 GRB detections, 25 solar flares. Also on this website, you can find the list of our detections and some basic data products, light curves, and some information about the duration of the GRB, so on. We also have some common detections between both satellites. This is the soft gamma repeater, which we observed with VESELSAT-2 and GRB alpha. And we were also, again, lucky because we also observed the second brightest GRB, 230307A, which was also a very interesting event. It was a long GRB, but with associated kilonova, which is due to a merger involving a neutron star. So, but it was a long GRB. And James WST also measured the spectrum of the kilonova and detected heavy elements like a tellur and wolfram. In near future, next year, we would like to launch GRB-beta, which will have some improvements. Detector will be basically the same, but there will be improvements on the satellite bus. There will be, we will have S-band communication. We will use attitude control. There will be infrared sensors for the sun to determine the attitude of the satellite. And we will test a near UV sensor on board provided by Luke's team from University of Toronto. And this will be very useful for the next mission for the cubic, for the UV small satellite mission. And we want to see how many cosmic rays we will detect, how the detector will age, and qualify it or test it in the space before it is launched on the bigger mission. So I think now I'm getting actually to the, for me, more exciting or more fresh mission. The cubic will have it is a small satellite, about 100 kilogram large. It will have on board about 30 centimeter diameter mirror telescope. We want to observe a kilonovae in 2 bands, in near UV and far UV. And the idea is to slew to positions determined by the gravitational wave observatories, do the scanning of the region, and try to find a kilonova. We will also follow other triggers. For example, LSST will provide many directions of a new transients. If Ultrasat is launched on time, then also we will follow the alerts provided by the Ultrasat mission, which is an Israeli-US mission. Also UV telescope with a much larger field of view, and they also aim for observing a kilonovae. The consortium is such that the prime contractor is the VESELU, which is the Czech Aerospace Research Center. We are at Masaryk University responsible for the science. The top tech company is responsible for the telescope design. It is a company which actually is under the Academy of Sciences. Then the Pegasat will be responsible for the ground communication. It's a Czech company. So the goal is to have much more observations of the electromagnetic follow-up of the electromagnetic counterpart together with the gravitational wave events. such as in 2017, the short gamma ray burst was observed. There was also gravitational wave detection, and then there was a large campaign to observe the light curves in different wave bands, and there was a kilonova observed, well known. And to do more, I mean, we need more regular detections to do the progress in the models of the kilonovae, to model the different models of the emissions in kilonovae. We choose our mission to be in near UV because it cannot be done from the Earth. And but this is challenging because in the near UV band, the light curve is decaying very fast. So the telescope has to be agile and within tens of minutes start measuring. And in one day, maybe in 2 days, the brightness in the near UV can already drop down below our sensitivity. So we will do the crucial observations in the first hours and tens of hours after the merger of the neutron stars. Doing the observation near UV can also help to determine distinguish between different emission models, like the nucleosynthesis powered kilonovae is shown here in the near UV and far UV. There can be also additional heating due to the decay of the free neutrons, which haven't been observed yet. And this can be additional component at the very beginning. So again, doing the observations in the first few hours will be crucial. There can be also a shock-powered component, this power law shown in the red curve. So far, we are about here, and the QUIC should be launched in 2028. Our goal is really to be in line with the 05 of the LIGO Virgo Cagra observing run, so we can do follow-up of the gravitational wave alerts. And the sensitivity should be enough to have several kilonova detections per year. This is a simulated image with a kilonova of the 21st AB magnitude at a distance of 200 megaparsec. Shifted, the star field is taken from the observation of the kilonova from 2017, and we offset the kilonova to the typical distance from the host galaxy of 1.5 effective Revue. This is for the short GRBs, which are coming from the mergers of neutron stars. We did also simulations of the kilonova light curves, where we took the POSIS-2 code and the results from this code made by Boolean, where we simulated the light curves. This plot shows the absolute magnitude as with respect to the time, and then we place the kilonovae in the sensitivity volume of LIGO expected in 05, and we need to. So our threshold will be around 22 magnitude, which means in 1 day within 1 day after the merger will be really the time where we can detect the kilonovae, and after that in near UV, the light curves will be too dim for us. This is of course just taking into account the nucleosynthesis powered kilonova. There is no additional brightening which can be there due to the decay of the free neutrons. And from these simulations, we obtained that there can be around 20 kilonovae per year, theoretically observable by QUIC, so bright enough to be followed. Another question is how fast we will be able to find the kilonova giving the error region from LIGO, or how effective will be other observatories providing the triggers and alerts for us. There will be lots of other scientific objectives because between the slewing to kilonova targets, there will be sources which can be followed. like a gamma ray burst, supernovae, novae. At our university, there is a strong group which is studying different types of stars. We will be also following AGNs and trying to find TDE events. Even exoplanets are in our program. Recently, we submitted 3 papers describing the science program for QVIC mission. So if you are interested in more details, you can find a lot in these papers. The mission itself, or the satellite itself, the satellite bus is developed by the Zulu. It will have a modular design, so it can be. It will have different devices on each side, and the satellite can be assembled in such a modular way. It can be also used for other missions. There will be also a mission called AMBITS, which will do Earth observations, and it's also a check mission, and it will have the same bus and same modular structure with just a different payload. The telescope itself, it's a diameter 36 centimeter. We will cover 2 bands, near UV and far UV, where the far UV is sort of optional. So we will see how challenging it is, and if it is much more challenging for the cleaners and also more costly. So this is something where we can see some. If we need to scale down the mission, we may drop down the far UV, but right now this is what we would like to have. The field of view will be about in near UV about 1.5 degree. The sensors will be either the CMOS from this G-Sense 4040. It is a 16 megapixel sensor, or a detector developed by DESI for the Ultrasat, and we have a collaboration with them, which may involve also the sharing the Science Operations Center together with the Ultrasat team. The sensitivity will be around 22nd magnitude, AB magnitude in 1000 seconds for 5 sigma detection. There is a strong international dimension of this mission because it involves also the gravitational wave observatories. We will be complementary to Ultrasat. Ultrasat will use different near UV band or lower energies. We will have a wider band, and if we have a far UV, then we will be fully complementary to Ultrasat because Ultrasat doesn't use the far UV. And also this is important. So QVIC will provide the open observing time for the international astronomy community through proposals. So if you have some topic which you want to study, you will be able to write the proposals and suggest the observing time. So in summary, the 2 CubeSats are so far very successful. GRB alpha observed more than 70 transients, VSAT-2 more than about 60 transients. GRB alpha is in space already for more than 2.5 years. We are studying the background and studying how the detector is aging. In near future, we will launch the 2-unit size GRB-beta. The QVIC is currently in the V1 phase. It was selected for funding. And if you are interested in more details, I will be here until Thursday, so we can discuss more details. And you can also look at these publications. And that's all from me, and I will take your questions.
We have time for a couple of questions. Let me see if either from the remote audience or from the room. Anybody?
Some curiosity, maybe as I missed, but about the performances of GRB alpha. So is it correct to state that the detection rate of GRBs is more or less 22, 25 per year? Something
Yes.
which is more or less 10 times less than the 30 GBM. Well,
Yes.
not normal.
But our duty cycle, the first year was very low. Then we did a firmware upgrade on board. So the first year we had like 5 detections. But after that, we were able to do data compression on board, and we are now observing 24 hours. So I think it's actually more than 20 GRBs per year, including. So it's like how much is it per year, including if I consider the full duty cycle, maybe 40 per year or 35. And about half of the time we are in the high background region where we cannot observe GRBs.
And about the timing capabilities typical of crystal scintillation, which is a few microseconds.
Yes.
And the data are always photon by photon, or it's only when there is a trigger?
It is binned, so we are actually binning the data on board, so it's not event by event. And we are collecting data with 1 second resolution. But we are working on improvement on the onboard software, or it's actually our colleague in Hungary is working on it. So because we would like to do the time for timing localization, you need at least 1 millisecond or tenths of millisecond. So this is not the final resolution which we would like for the following missions.
You are not constrained up to now by the telemetry capability. It's more the onboard software.
I think it's more the onboard software. And actually, we don't have even trigger on board. We are recording data and check the other missions. If there is other mission detected to GRB, then we just download the section of the day of our light curves and then look for them. So this is also for the future. We would like to upload the trigger algorithm on board.
Okay, last question.
I don't know if I'm allowed to ask this, but when building small satellites, something that is quite important when you want to launch new versions is the total cost of the model. No? Like one of the biggest advantages of launching small CubeSats is the fact that they also cost much less than a medium or large mission. Which is more or less the implicit cost of GRB alpha? What do you expect from GRB beta, more or less?
I don't remember exactly because I actually the head of our group remembers much more this because he had to cover the cost. But I think it was for GRB alpha around 150,000 euro.
It's a nice cost. It's like very much cheaper than traditions.
We actually won a big discount for the launch.
Oh.
Yeah.
And then regarding cubic, I was talking to Lorenzo just now that it seems to be a very good mission concept, to have synergies with all the follow-up missions for gravitational waves. No? Like here we are working with the CUs, and we expect the CUs to be very important. If it gets launched, to be very important finding the counterparts of Illinois. And I was thinking that cubic resembles a bit more like a newer Swift, no? In the sense that you have the ultraviolet band that you don't have. So if you expect to launch it in 2028, so I think it was the year, other than the gravitational wave detection itself, which other observatories do you expect to have synergies with, like to find the counterparts? Because you were saying it depends highly on how do you reduce the error area of the LIGO.
Yes. So yeah, our field of view will be larger than for Swift. That was for Swift is 17 arc minutes, if I remember correctly. But it's not large enough for do the survey of the sky. So we really need synergy with Ultrasat and with the ground observatories. So mainly I think LSST. So it is possible that someone will find a kilonova with the visual band earlier and send a trigger, and we will do follow up in the UV.
Yeah, because you mentioned it very quick to the big point to flu. So
yes, it will not be as fast as Swift. So we aim for, I think in our requirements is to start observation 20 minutes after receiving the alert. Our engineers are saying it will be possible to be faster, maybe like 5 minutes. But it's slower than Swift, but relatively fast. Yeah, it would be really interesting to have a synergy with Theseus. I don't know if so there will be the SWAM mission. I'm not sure if they will last until the cubic. Let's hope yes. I think they will be launched next year.
Okay. Thanks. I think that's it for today. Thanks, speaker.